Greetings, chemistry students. So today I'm going to be redoing the reactants in a 1-to-1 ratio for finding the limiting reagents. I'm skipping the squares and triangles stuff just for the sake of kind of cutting to the chemistry and getting that stuff done. So here we go. The first thing I'm going to point out is that I balanced the chemical equation. We have all ones as our coefficients in front of our chemicals, which is going to make things really easy down the road for us. So the first thing I'm going to do is I'm going to take and find the amount of moles of silver nitrate I have. And I'm doing this with silver nitrate because and the big giveaway for these type of questions is that they tell you have 10 grams of silver nitrate and 10 grams of sodium chloride. And when you have two masses given and they're both products, or sorry, they're both reactants, it's asking to figure out which one of these two is going to be limiting the reaction. So which one of them they're limiting reagent? Which of the two reactants is going to control the reaction because there's less of it? So you can't just look at the mass to figure out if there's less of it. You have to convert the mass to moles. So I have 10 grams of AgNO3, and I divide by the molar mass, which is 169.88 grams per mole, which gives me 0.05887 mole. That's a bit messy. Mole of AgNO3. So I'm going to redo what I just did with sodium chloride. Sorry, I had to sneeze. So I'm going to find out how many moles of sodium chloride I have. My mass of sodium chloride was 5 grams. Divide by the molar mass of molar mass of sodium chloride, which is 58.44 grams per mole, which gives me a grand total of 0.8556. Sorry about that. If you're I made a mistake there and I can't erase it because I pressed the wrong button. But 0.08556, and I can't get my pen to write right over top of that decimal, but that's a 0 right there. 0.08556 moles of NaCl. So since it's a 1-to-1 ratio of AgNO3 to NaCl, we can compare these amounts just as they are. So since reactants are in 1-to-1 ratio, the limiting reagent is AgNO3. How'd I figure it out? Well, you'll all agree that this number is smaller than that number. And that's the long and short of it. So in this situation, the first thing you should do is balance your chemical reactions. So I've got 1, 3, 2. So now that it's balanced, I can now move forward. And I just wrote my 1 for the sake of it. You don't have to write your 1 in there. So just like before, I'm going to take my masses, and again, you know that you're going to be having to compare to your two reactants because you've got mass of nitrogen gas and mass of hydrogen gas, and that's you for what's the limiting. So we have to take these two and figure out which is there less of in terms of moles. You can't compare mass to mass. So my moles of hydrogen gas equals 26.00 grams divided by the molar mass, which is 28.02 grams per mole, which gives us 0.9279 mole of N2. And then if we look down here, we can look at our amount of hydrogen gas. Sorry if that's messy up there. That should look more like nitrogen gas. if I said hydrogen gas, I'm sorry, but I meant to say nitrogen gas. So if we look at our amount of hydrogen gas, that's going to be 3.00 grams of hydrogen gas divided by the molar mass of hydrogen gas, which is 2.02 grams per mole, which gives us 1.485 mole. Why did I only write 3 decimal places? Because there's 1, 2, 3, 4 significant digits. Don't be fooled. That's moles of H2, and oftentimes people look at that and say, all right, good, this is easy. I know obviously that here's our limiting reagent right here because there's less of it and there's more of that. But in this situation, we aren't on a 1-to-1 ratio. It's some other ratio. And when this is the case, we need to figure out, how much of the opposite is needed by converting one of the two. So you pick one of the two. In class, we picked a nitrogen gas. So I'm just going to repeat what we did in class. So what you're going to do is you're going to figure out how much hydrogen gas is needed using your mole ratio. So you have N2 on the top. You are going to put moles of N2 on the bottom. And what you're going to look at is you're going to look at the chemical equation at the top. And if you have moles of N2 here, how many moles? 1. And so for every 3 moles of hydrogen gas, you are going to need 1 mole of nitrogen gas. So you do this math. You go 0.9279 times 3 divide by 1, and what you should end up getting is you should get that 2.784 mole of H2 is needed. Well, now you're ready to compare. So here's the amount of H2 have. So this is what you have, and this is what you need of hydrogen gas. Do you have enough is the question. No, you do not. So therefore, this is your limiting reagent. So I'm going to have to remember that number because on this I'm going to flip the page or I'm going to go to a new slide, but on the worksheet or on the note we did, I just moved down. So I'm going to take this number here and I'm going to work with it. You do not work with how much is needed. You work with what you have, okay? So you take what you have. Now we're going to take that and we have with 1.485 moles of hydrogen gas. And if you remember from before, I'm a really big fan of that roadmap. So I've got nitrogen gas plus 3 hydrogen gas reacting to form 2 ammonia gas. So what we're doing now is we need to figure out the theoretical yield for ammonia. And this is a big important thing. So we're going to use our limiting reagent, which is hydrogen gas, and basically we're already at mole. So in terms of the mole roadmap, I'm down here at mole. I'm going to convert over to moles using mole ratio, and then I'm going to convert moles to mass to get my final theoretical yield. So I take my 1.48, I now multiply by mole ratio because I am at moles and I want to get to moles. And how do I do that? Mole ratio. So I put moles of hydrogen gas on the bottom, and my number of moles of hydrogen gas are 3 moles, and the ratio would be 2 moles of NH3 for every 3 moles of H2 gas. I've run out of room on the side here, but what I can do is I can kind of work below and get 0.9900 moles of what, I wonder? Well, I cancel out those two and I know that I'm left with moles of NH3. Beautiful. So now in terms of our mole roadmap, we've converted from moles to moles. Now we've got to go from moles to mass. How do you go from moles to mass? Why, yes, you multiply by molar mass. So I take my 0.9900 mole, and what I do is I now multiply by the molar mass of ammonia, which is 17.04 0.4 grams per mole. Our moles cross out, leaving us with 16.87 grams of NH3. So when we do our therefore statement, we go all the way back to the start. At the very, very start, we were told 26.00 and 3.00 grams. In 26.00, there's 4 significant digits, and with 3.00, we have 3 significant digits. We have to use the least number of significant digits to report our answer. And so therefore, the theoretical yield is 16.9 grams. And I'd write that out a lot better, but I'm trying to get over to the next part and kind of finish this all out for you folks. Okay, so actual yield, percent yield equals actual divided by theoretical. So what you just calculated using stoichiometry and limiting reactions is your theoretical yield, and that's what in theory you should get. Actual yield is what you do in a lab. So if you make something in a lab, that's your actual. What you predict using stoichiometry is your theoretical. So I would say percent yield equals 15.8 grams divided by 16.9 grams equals times 100 equals 93.65% yield. So I can then make my therefore statement. Therefore, 93.7% yield was achieved. Sweet. 93%. I'd be pretty happy with that. Okay, so now we have to figure out how much nitrogen gas is in excess. So you knew that hydrogen gas was our limiting reactant, and now we have to figure out how much nitrogen gas is left over because it was in excess. We had just the hydrogen was controlling the experiment. Once we ran out of hydrogen, the reaction stopped, which means that we'd obviously have leftover nitrogen. So if you look way back up to the top of your note, you'll notice that we calculated that our moles of nitrogen gas was equal to 0.9279 moles. Perfect. So then what we have to do is we need to figure out our amount of nitrogen gas needed. Now sometimes you might have done this way back a couple slides ago when you calculated the moles of hydrogen, and then you may have figured out just by chance the moles of nitrogen needed, and by reading ahead you can kind of strategically pick what you want to do. I'm going to have to do a little bit of math. So you know that you needed, so I'm going to kind of do my work down below here. I'm going to say that, well, originally we had 1.485 moles of hydrogen gas, right? Now we're going to figure out how much we needed of nitrogen gas. So for every 3 mole of hydrogen gas, there's 1 mole of nitrogen gas. Cancels out. And when I punch that into my calculator, I get 0.4950 mole needed. And that's going to be how much is used up. So I take this number that I just got, 0.4950 moles. I subtract that from what I had. So 0.4950 mole. So to review, this is what was needed. Oh, sorry, this is what I have. Sorry about that. This is what I have, and this is what I needed. And this was all that was used. Once we used that 0.49 moles, then we're in that situation where the reaction stops because we've run out of hydrogen gas. So what's going to be left over? It's going to be left over with, and I've run out of room over here on the side, so I can't really work there, but if you have room, you can keep going. We got 0.4329 mole of N2 that remains. Well, that's not really that helpful. Let's convert it to grams so we can at least understand that number. Times 28.02 grams per mole. I'm running out of room here. And that's going to equal 12.13 grams. So we can take that and say, well, finally, there remains 12.1 grams. Why only 3 digits? Well, if you look way back at the top, we were only using 3 significant digits when we said 3 grams. There remains 12.1 grams excess nitrogen gas.